Hello all, my name is Federico di Vruno. I am Spectrum Manager at the SKA Observatory and co-director of the IIU Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference, or IIU CPS. I will talk about the impact of large satellite constellations on radio telescopes, overview, and mitigation strategies. Okay, so let's start with a brief introduction to satellite constellations or large satellite constellations. Groups of satellites are not a new thing for radio astronomy. Since long, we have global navigation constellations and some communication ones like Iridium, Orbcom, and others. But advancements in technology have enabled a new generation of constellations in low Earth orbit, with thousands of satellites each one. Since the last 3 years, when these constellations started to be deployed, the number of satellites in LEO has been increasing almost exponentially. In this table, you can see some of the current and planned constellations in LEO, including Starlink, OneWeb, Kuiper, and some others. And this is not even an exhaustive list. Note that in the last column of the table, the downlink frequencies of the satellites are listed. Most of them fall within the frequency range of both the SKA-Mid and the NGDLA, and in addition, almost all of the downlinks of satellites are adjacent or close to primary radio astronomy allocations, like the 10.6 to 10.7 GHz, 22 GHz, 43 GHz, and 77 GHz. So how does a radio telescope see these satellites? You can see here an animation showing the received power by a radio telescope using a simplified antenna model from the ITU, where in the top panel this shows the satellites moving in the sky in azimuth and elevation, and in the lower panel is the total received power from all the visible satellites. If you look carefully, you can see that when a satellite passes near the red bright spot, where the telescope is pointing in azimuth and elevation, a very strong signal is received. But also, all the other satellites above the horizon are contributing to the total power. Note that in here, satellites are just modeled as simple isotropic transmitters. So how can these satellite constellations impact radio telescopes? I have classified here the effects by severity, with the exception of the last one, which requires further studies. The first one is damage to a receptor, as when beam-to-beam coupling occurs. While radio telescopes have a very large gain, the power flux density produced by these satellites on the surface of the Earth is not enough to reach dangerous power levels at the first LNAs. Number two is saturation or nonlinearities. This is a very important one because if signals are very strong in a portion of the bandwidth of the receiver, they can saturate or produce spurious components or frequencies that can contaminate the complete receiver band. This could result in effectively losing the complete band for the duration of the event when the satellite goes by the beam, or probably more. We will dive into this one later. Number three is related to out-of-band emissions of downlinks, where these can fall into primary radio astronomy bands, contaminating them. This aspect is normally addressed by spectrum managers at regulatory forums such as the International Telecommunications Union or the European Regional Group called CEPT, where the report ECC 271 was produced to study the protection of the band 10.6 to 10.7 GHz. Hopefully, we will be seeing updates of this report soon with new constellations and their frequency bands. Number four is about undesired signals, not to call them RFI for a moment, in wideband observations, meaning that if a receiver is not saturated, it will still see signals in the downlink frequencies of the satellites. And the last one, marks as second-order effects, is related to unintended emissions from satellites or reflections from strong terrestrial signals. These two have only been theoretically discussed so far and require further observations and studies. In this presentation, I will focus on the second and fourth effect only due to time availability, but feel free to contact me if you're interested in the others. So let's start with the first one. Okay, so saturations or nonlinearities in receivers. As you saw before in the animation, when there is a satellite close to the telescope beam, a very strong signal is received. The question is, since all these constellations have different numbers of satellites and orbital parameters, how often can a radio telescope have a satellite that close? To estimate this, we must choose what close means, right? We must choose an angular distance. In this case, we took 0.5 degrees or a 1 degree beam width. Also, we need the location of the telescope, so we will choose, of course, the SKA-Mid and the NGVLA cores and each constellation parameters. Well, one can think that 1 degree is a very broad beam for a 15 or 18 meter parabolic antenna at about 11 gigahertz. This angular separation still produces a significant gain, which combined with the maximum power flux density of the satellites on the ground can cause saturation or nonlinearity problems. By propagating each constellation in hundreds of time steps in thousands of repetitions with different starting times, we can estimate how the satellite density in the local sky will look like. You can see that for Starlink Phase 1, the density is higher towards the north at the NGVLA site and towards the south at the SKA-Mid site. This is due to the 53-degree inclination of the planes in this constellation. The same happens for the constellation Starlink Phase 2 and GO1, where you can see lines with higher density representing some of the planes of these constellations with different inclinations. A special case is OneWeb Phase 1, which has not only less satellites than all the others, but also has polar orbits. And so the satellites move only from north to south or vice versa. You can see also here that the average number of satellites that an antenna or of a 1 degree beam width in this case will see increases with the number of satellites in a constellation. But it also depends on its orbital parameters and the latitude of the observer. It's also worth noting that while the average value might not look too big, like in the case of GO1, for the 0.013 satellites per second, or one satellite every 77 seconds, but some areas in the sky can reach up to one satellite every 16, sorry. If one adds all the densities together, Starlink Phase 1 and 2, OneWeb Phase 1 and 2, and GO1, we end up with these results, where you can again see the characteristics of the northern hemisphere in the NGVLA site and the southern hemisphere at the SKA-Mid site. This shows that on average, one satellite will be within 0.5 degrees of the antenna bore side about 4% of the time, with areas of the sky where the density will be much higher, of course. Just as a clarification, the lowest elevation used for this calculation was 15 degrees. Of course, lower elevations can have many more satellites, but radio telescopes will rarely point there in practice. Okay, but what does this 4% really means? Considering the power flux density of these downlinks and the gain, for example, a 15-meter dish like the SKA-Mid, but truncated at the angles we were talking about, the receipt power from a satellite can be calculated. This can then, for example, be compared to the integrated noise power of a 20 Kelvin and 5 gigahertz bandwidth receivers. These are the SKA-Mid approximated values. And by comparing these two results, we obtain the necessary dynamic range for several boreside angles to accommodate the RFI signals that are received, assuming, of course, that the receiver is adjusted to sample only white noise if there was no RFI. Therefore, what this table is telling us here is that for 0.13% of the time, a 41 dB dynamic range will be needed to sample the RFI correctly, right, to not saturate. Same 19 dB will be needed for 3.8 or 4% of the time, and 14 dB for 11% of the time, and so on. Of course, with the assumptions we've been using so far. Okay, so depending on what is the available dynamic range of the receiver, some kind of mitigations might be needed. So what can work in this case? A few things can be done, like, for example, having the satellite operator to avoid the core and individual antennas of interferometers. For example, Starlink is already doing this in several countries, like in the US, in Germany, in Spain, and others, where they are putting circles in their coverage to protect radio telescopes. Or coordinating the dynamic pointing of satellites so that the satellite in the main beam of a telescope is pointing away of the telescope. This last one would require significant coordination between the telescope and the operators, of course. And the last one could also be increasing the dynamic range of receivers, which, as you might know, is already extremely difficult for the frequencies and the bandwidths that normally radio telescope receivers use. And of course, it could result in a very large cost for observatories. So let's suppose that it's possible to avoid the telescopes so that the power is reduced by about 20 dBs or 100 times. Then the extra dynamic range would only be required for a very small boresight angles with a very, very low probability of occurring. So one could almost ignore this case marked in yellow here. In this situation, almost no linearity issues would occur if one can lower the power flux density by 20 dB. So now let's consider that the receiver is not saturated. All the band is sampled and channelized correctly. There will still be very strong signals, of course, for radio astronomy standards within the satellite downlink bands. So the question is now, what can we do in these bands for radio astronomy? One important consideration is that these are satellite downlink bands assigned to the fixed satellite service by the International Telecommunication Union. And radio astronomy observations are conducted there on opportunistic basis. But of course, in the case of SKA-Mid, this is different, as our radio telescopes are located in a radio quiet zone. We have made a calculation of the equivalent power flux density received from Starlink phase 1 and OneWeb phase 1 by an antenna of the SKA-Mid using published satellite antenna models, and this resulted in fluxes in the order of 1,000 Janskis. Again, this is in the satellite downlink bands. So 1,000 Janskis is, of course, quite a strong signal, so in this case, what mitigations are possible? On the telescope side, a prediction tool can be used to optimize observing plans, for example, avoiding areas of the sky with high satellite density or masking challenging time when satellites are nearby. This type of tool requires high precision ephemerides from the operators, and so far SpaceX and OneWeb are updating this a few times a day. The SatHub area from the IAU CPS is working on developing a software called PassPredict and studying the accuracy of ephemerides to be used by astronomers. Another possible mitigation tool on the telescope side is using online flagging and excision tools. This can avoid strong RFI events in channels used by satellites, lowering the amount of RFI integrated into visibilities. Of course, this flagged data can represent the data loss in these frequencies. In the study we conducted for the SKA-Mid antennas, about 4% of flagged data was estimated across the sky in coarse channels with Starlink phase 1 and OneWeb phase 1 constellations. And once this RFI flagging and excision is applied, residual RFI or leftover RFI will be still remain, right? It's the things that the automatic flagging could not detect. So this is related to power received through the side lobes of the telescopes coming from probably the satellite side lobes or satellite main beams. And this residual RFI can affect observations in different ways, right? Probably incoherently, increasing the system temperature or decreasing the available bandwidth, or resulting in more time observing for the same sensitivity, or coherently, where the residual RFI can still remain even after cross correlations. The third possible mitigation is to actually coordinate frequencies with the operators. Operators could clear one or a few channels for the duration of an observation to later use them while the telescope is operating in another band. This has the benefit of more efficient spectrum use and a guaranteed clean channel for observations. Like, for example, this example where you can see just a box where the vertical axis is time, and this is marking just one channel. But this includes the complication of coordination between the telescope and the satellite operators. Research is ongoing in this area, but these are early stages. And the last and most obvious one is using interferometers, where very long baselines could attenuate downlink signals significantly. This is of course very useful, but could be less effective in the course of interferometers where the short baselines, and in some observations where just interferometry is actually not used. So to conclude, I would like to remark that while this is a challenging situation, mitigations are possible to lower the impact of all these constellations on telescope operations. Measurements to verify assumptions and models are ongoing, but this takes time and effort. Ongoing monitoring will be very important to ensure the protection of the, first of all, radio astronomy bands, as observation channels guaranteed to be clean. These are very important bands, and to monitor site protections where in place. Research is also, of course, needed. Many topics are under study, like aggregate effects of different constellations, predictions and simulations, especially of the new constellations in higher frequency, are required, coordination with operators, and RFI mitigation. For your attention, and hopefully I will be connected to answer any questions you have. Thank you.
Great. Are there questions for Federico? Oh, yep.
Hi, thank you. I think a lot of us are maybe aware that when they say they'll emit in certain frequencies, there's often leakage into neighboring frequencies quite often. Are there any plans to discuss with these companies whether they'll test their equipment so that it won't leak, or it will leak, you know, with some constraint?
Can you hear me okay, by the way? Yeah, good. I see people nodding. Thank you. Apologies not be there. Good question. Very interesting, and that's true, right? Any normal real signal has some leakage outside of the allocated band that they have. At the moment, the challenge for us as radio astronomers or in radio astronomy is that all these limits for satellite operators are defined in the ITU and are defined in communication standards, right? So what we consider strong emissions are very low emissions for satellite standards. And so there will be leakage signals. And at the moment, I know many people is working on this. We are also working on this, trying to make measurements, actual measurements of what the satellites are transmitting right now for some of these constellations that are up there, like Starlink phase 1 and OneWeb phase 1. And we are trying to characterize this. What they are trying to do right now is pretty much following what the ITU says, the international regulation. And this is protecting the radio astronomy bands, right? The challenge is that these bands are very small, and compared to the receiver bandwidth we have, are really, really small. But just to have an idea of what is the level of out-of-band emissions of these systems, there was a study done with many assumptions in there, but the result of the study was that in order to protect the 10.6 to 10.7 gigahertz band, neither OneWeb or Starlink phase 1 could use the immediately adjacent channel, the one that goes from 10.7 to 10.9, something like that, 250 megahertz. So yeah, long story short, there are out-of-band emissions, and we will see them, definitely.
We need to move on here, so I'm sure Federico is available on Slack.
I'll be on the Slack, yeah.
Start a conversation. So let's thank Federico again.